Hello, my name is Santiago Mol Lopez, and in this video we are going to define the polynomial functions and study the graphs and main properties of the polynomial functions of grade 0 and grade 1. The requirements are quite basic. You should know the concept of function, know how to work with powers, and solve linear equation systems 2 by 2. Two equations with two unknowns. A polynomial function is the following. We have some strange numbers in red: a sub n minus 1, a sub 2, a sub 1, a sub 0. And x raised to n minus 1, x squared and x. As you can see, the exponent of the x is decreasing, and these subscripts go according to that. The important thing you should know is that the values in red are simply numbers, which are real, although they may not be real. In this case, we are going to work always with real numbers. They are constant and are called polynomial coefficients. Let's examine examples of polynomial functions. It's relatively straightforward to verify their polynomial nature. In this case, just to give a small example, we will study which are the coefficients of each one. In the first example, it would be 1, which is the number that multiplies x cubed. 4 would be the next coefficient, 2 and 1. This function is very simple, it's x squared. Here we can also study the coefficients that would be 4 minus 2 and 4. What is the degree of a polynomial? It is defined as the greatest exponent of the expression, so that the coefficient of that power is different from 0. Why is this last sentence important? Let's go back a little and explain it. I could put this polynomial in one more term, which would be as follows: plus 0 by x to the fourth. But 0 by x to the fourth is 0. When multiplying by 0, I have nothing. I can't say that the degree is 4, because the coefficient that multiplies x to the fourth would be 0. So what is the degree of this polynomial? Let's go straight to the point. This degree is 3, this one is 2, and this is 5. It is the highest exponent, okay? The domain of a polynomial function is, as long as it is not the opposite, that is, restrictive in the problem, is the set of all real numbers. Remember that the domain is the set in which the function is defined, where there is no problem. And the polynomials can be calculated at any value of x, at any value of the real numbers. What about range and continuity? You must know, although I don't know if you remember the continuity and the range, that any polynomial function is continuous over its entire domain, and that its range is normally all the real numbers, or its subset. For example, in this case, let's go back a little. The range of x squared, which is like its image, is only the positive real numbers. Why? Because when squaring any number, it always gives me a positive. And the fact that it is continuous, well, the explanation is quite long, and we would not have enough time in this video, but it is enough to say, in a slightly easy way, that a continuous function could be represented without lifting the pencil off the paper. The important thing is that the polynomial functions are always continuous, and that you must remember. Let's see examples of polynomial functions of grade 0. What are they really? In reality, they are constant functions, where k here can take any value. Examples of constant functions: y equal to 0, y equal to 3, y equal to 7, and its graphic representation, as you can see, are simple. They are horizontal lines on the axis. Notice that this would be the x-axis and this y-axis. They are simply horizontal lines. Let's talk now about polynomial functions of grade 1 called finite functions. They are functions of the form ax plus b, where the grade is 1, as you can see, and a must be different from 0. Because if it is equal to 0, we would talk about a constant function, which is the previous example. The properties. Its domain includes all real numbers, and its graphs consist of lines that are not parallel to the coordinate axis. A is the slope of the line, and b is the coordinate in the origin. Let's see examples of finite functions. As you can see, in this case, we have x plus 1, 3x minus 2, minus 9x plus 4. Remember that a is the slope of the line, so which is the slope of these lines? It is 1, 3, and minus 9. And the coordinate at origin, which is the b. In this case, it would be 1, minus 2, and 4. What happens when we represent these functions? We need to observe the resulting lines. Although it is not very visible, y equal to x plus 1 would be the blue, y equal to 3x minus 2 would be the one which is a little more purple, and minus 9x plus 4 is the one that goes down. Have you noticed that the slope of the first one was 1 and it goes up? The slope of the second one is 3 and also goes up. The function is growing, and it grows a little more than the other. That is, the slope is a little bigger. And the last one has a negative slope, and therefore the function is decreasing. I hope you observe it, because it is quite important when drawing lines. Particular cases. We are talking about affine functions. As you can see, ax plus b. What happens when b is 0? That is, when we have functions of the form a by x. In this case, the graph passes through the origin, obviously. If I set x to 0, the product of 0 and any value of a is 0, so it passes through the point 0, 0. In other words, all functions of this form pass through the origin. Some examples of these functions, here you have them. X, 2x, 3x minus x. The slope of these straight lines is 1, 2, 3, and minus 1. Let's see how is the slope when functions pass through the origin. Here you have it. Let's see. Y equal to x would be the blue that you have here, this main one. As you can see, this more or less would be inclination 1, slope 1. And notice that this straight line goes through the 2, 2, and 4, 4. So, this is the slope 1. The next one is equal to 2x. Which one is equal to 2x? It would be this one here. The one that goes on, this one here. The one that is a little more reddish. In this case, as you can see, the slope is slightly greater than 1, suggesting a slightly steeper incline. The one with a slope of 3 is slightly more inclined than the previous ones. And the one of y equal to minus x, which has slope minus 1, which is decreasing, is this one here, which is green. If we represent the following functions, now we will see what happens when we have the same slope. These cases are when the slopes change. These cases are when the slopes are exactly the same. However, we change the coordinate in the origin. What do you think will happen? All of them have the same inclination, but they are going to pass through different points of the y-axis. Look, y equal to 2x is the blue one. Y equal to 2x plus 1 would be the next one that you have here. And y equal to 2x plus 2 would be this one here. I don't know if you realize, but look, the first one, y equal to 2x goes through the origin. The coordinate in the origin was 0. See? It goes through the origin. The next one is 2x plus 1. This one goes through this point, 0, 1. This one represents this one here. It goes through this point. It cuts the y-axis in that point. And in the last one, y equal to 2x plus 2, as you can see, it cuts the y-axis at point 2. Good. Parameter determination. As the affine functions depend on two parameters that have been determined by 2 points, a single line passes through 2 points. If we give you 2 points, you can find the equation of the line. And that's what we're going to try to do at this moment. Determine the equation of the affine function, which graph goes through the points, minus 1, 2, and 3, minus 1. Or they give us the points, I insist, a single line passes through 2 points. Therefore, we're going to find out what line it is. The equation of an affine function is y equal to ax plus b. If it goes through the point minus 1, 2, we have that this equality is fulfilled. But where does this equality come from? We're going to go a few seconds back. These are the coordinates of a point. This is the component x and this is the component y. Therefore, if you return to the affine function that you have here, what we actually do is replace the y by 2 and the x by minus 1, forcing this function to pass through the point minus 1, 2. Do you see? We have 2 that equals the y. It is equal to a by the x, which is minus 1 plus b. If in addition this line has to go through the point 3 minus 1, we do exactly the same. This is the component x and this is the component y. We replace the y by minus 1 and replace the x by 3. We will obtain this equation. What is this? This is a system of two equations with two unknowns. If you pay attention, if we simplify a bit here, this part of the equality is written on the other side to make it more standardized. But it is exactly the same system. A by minus 1 is minus a. So I have minus a plus b equal to 2, and that 3a plus b is equal to minus 1. The solution of a system of two equations with two unknowns can be resolved in 1,000 ways. In this case, you can use the system of reduction, substitution, equalization, even Gauss if you want. I have done it here simply by substitution. It results in a being equal to minus 3/4 and b is equal to 5/4. If you do not remember well, try to practice it and check that you get the solution. If now we replace the value of a and the value of b in the formula of the affine function, I obtain that the affine function that I was looking for is minus 3/4 of x plus 5/4. This line passes through the points minus 1, 2, and 3, minus 1. If you want, you can replace the value of x and check that the value of y comes out perfectly. What have we seen in this video? We have seen the definition of a polynomial function, how to graphically represent the polynomial functions of grade 0, constant functions. We have also seen the polynomial functions of grade 1 and its graphical representation. I hope you find all this helpful. Thank you very much for your attention.